Okay, let's move along with this solar radiation and greenhouse effect. We already saw this relation. I think I didn't mention explicitly that this is what is called the Stefan Boltzmann Law. So it's basically black body radiation, but once you add transmittivity, which can go from 0 to 1, then it's not a perfect black body anymore. A black body is something that absorbs all wavelengths and then emits all wavelengths. So the main thing to remember is that Earth is emitting as a black body, though not perfect, and the energy that goes out is proportional to fourth order of temperature, T to the fourth. Okay, that's something important to remember. So if we look then at radiation transmitted by the atmosphere, we already saw another version of this where we are now saying Sun is sending out radiation with this Planck's curve at 5525 Kelvin, and there are a bunch of greenhouse gases that affect the radiation at shortwave that's coming from the sun. So what reaches the surface is shown in these red in this red curve as we saw before. So UV, the atmosphere is almost completely opaque even though it's UVC, so A and B still make it to the Earth. 70 to 75% is transmitted to the surface in the visible band, and then you have some other longer wavelengths, and then the outgoing or upgoing thermal radiation by the Earth is in the infrared range, much longer wavelengths as we saw before, and 15 to 30% of that is transmitted. So you can see multiple Planck curves here in the range of 210 to 310 Kelvin. So obviously, as we said, the energy is proportional to wavelength, and inversely proportional to wavelength, and the total energy emitted can be fit to a maximum temperature with these kind of curves that we talked about in terms of the Planck's function. Wien's law gives you the maximum wavelength at which the energy is transmitted, and so on and so forth. So looking here at radiation transmitted and absorbed by the cloud-free atmosphere in this case, the left part of the figure shows solar radiation and the right part shows the Earth's radiation, so they are quite completely separated by wavelengths. The black body curve at 5525 Kelvin represents the incident downgoing solar radiation at the top of the atmosphere. The red filled area is the radiation transmitted through the atmosphere. The difference between the two, the white area between the red curve and the red area, is the amount absorbed by the atmosphere. For Earth's radiation, blackbody curves are shown for three temperatures, 210, 260 and 310 Kelvin, and represent outgoing radiation from the surface. Okay, so some of the energies being reflected by what we will see soon as Earth's albedo, about 30%, so only 70 to 75% is kept in the system. Out of that, the atmosphere absorbs some and some makes it all the way to the surface. So atmosphere gets warm by the energy absorbed and the surface gets warm by the energy received. And of course a lot of it goes into evaporation and so on. So how the energy gets distributed once it's come in is another issue. But whatever is happening when temperature changes because of the energy that has come in is going to determine how much of the long wave energy is going back out. So we are looking at 210, 260 and 310 Kelvin radiation energy bands here. So here you can see the wavelengths again going from 0.2 to 70 micrometers, and you can see the percent and the major components. So total absorption and scattering is being here. So obviously in the short wavelengths the energy is absorbed and this is where the energy is coming. Basically zero is absorbed, and you have various bands here that relate to water vapor, carbon dioxide, oxygen and ozone, methane, nitrous oxide, and what is really scattering. So we will see what are the scattering things in the atmosphere. You can imagine that there are dust particles, there are sulfuric acid and other things that scatter. So we will see what aerosols are in addition to the greenhouse gases. So this gives you a sense that greenhouse gases are going to be affecting the outgoing long wave, and the so that depends on where the wavelength is. So water has many bands in which it affects short wave and long wave. So this wavelength is almost continuous, so you have to be careful. So here we are not seeing the wavelengths, but you know that this is a short wavelength, these are the longer infrared wavelengths. So carbon dioxide had multiple bands, oxygen and ozone, so they absorb in the very short band energetic UV in the stratosphere, as we said. There are reasons why ozone is produced in the troposphere as a part of the pollution, and that's not good, because that not only affects health but also affects radiation. So it absorbs radiation if it is in the troposphere. It's good in the stratosphere because you want it to absorb UV, which will harm us if it comes through. But if ozone is in the troposphere, then it is a greenhouse gas, so it absorbs energy going out and creates warming. Okay, methane has a couple of bands here, nitrous oxide, and so on. So we will see that when we talk about global warming, we will have to talk about the concentration of these greenhouse gases and something called residence time, how long they stay in the atmosphere once they are put into the atmosphere. CO2 from fossil fuel burning, methane typically from coal burning or from wetlands, from cattle and so on, nitrous oxide from agricultural activities, etc. So how powerful they are as greenhouse gases, let's say, compared to carbon dioxide, and how long they stay. So we will see that that matters as well, and how much concentration there is. Okay, so this figure is basically showing a composition of the dry atmosphere. Water vapor, which is not included in this image, varies widely, but on average makes up about 1% of the troposphere. Why? Remember the Clausius-Clapeyron we saw before? As temperature increases, atmosphere's ability to hold water vapor increases, which means when you go to higher latitudes, in the polar latitudes, the atmosphere is very cold, so it hardly holds any moisture. Tropics are warm, so there is a lot of moisture in it. So water vapor has a large gradient in space, both in the vertical and in the horizontal latitude and longitude. So that matters because water vapor, which is a very strong greenhouse gas, is not uniformly distributed. Plus, it responds to temperature change. As we said before, if carbon dioxide increases, air temperature increases, water vapor increases, which causes more warming, so there is a feedback. So it's called a feedback gas. Okay. In the top right, we will see vibrational modes of CO2. The black circles in the center represent the carbon atom. I'll go back and show the figure, which carries a positive charge, whereas the oxygen atoms carry negative charges. So you have the dipole moment. As we said, symmetric molecules like N2 and O2 do not tend to have dipole moments, so they do not interact with electromagnetic radiation, so they are not greenhouse gases. The asymmetric stretch mode and the bend mode lead to an electric dipole moment. So when the energy is absorbed, it begins to have dipole moment because the symmetric calculation is symmetric cancellation doesn't work anymore. Whereas the symmetrical stretch A does not. Modes B and C correspond to absorption peaks around 4 and 15 micrometers respectively. So there are certain wavelengths at which the energy photons are able to excite the carbon modes, and that increases kinetic energy, which means it increases temperature. Okay, that's the main idea of greenhouse warming, right? In the bottom right, we'll look at vibrational modes of water. The red balls in the center represent negatively charged oxygen atom, whereas the white balls represent the positively charged hydrogen atoms. Due to its angle, it has a permanent dipole moment and various modes of vibration and rotation. So here we are. Dry atmosphere, water vapor is not included here. So you have nitrogen, which is 78.084%. Oxygen is almost 21%. Of the remaining, you have argon, which is almost 1%, and then you have CO2, H2, krypton, neon, helium, methane, etc. naturally occurring. The main thing to remember is that CO2 is a trace gas already, which is 0.04% of the atmosphere, and yet we have to worry about it because it's a powerful greenhouse gas. Methane, which is in parts per billion, so it's 0.0018%, so you can see it's clearly a couple of orders of magnitude smaller. So this is typically we talk about in parts per million by volume, whereas for methane, N2O, etc., we talk about parts per billion of volume. Okay, so here are the CO2 molecule, carbon and oxygen. So this stretch mode has no issue, but when you have bending mode and so let's go back here, make sure. So the bend mode and the asymmetric stretch mode. So symmetric stretch mode doesn't do anything. The asymmetric stretch mode and the bend mode can absorb energy of the longer wavelengths or outgoing long wave radiation at certain wavelengths. And this is the water molecule which is permanently bent like this, 105 degrees, and you have it's a dipolar molecule, so it's a very strong greenhouse gas, but as we said, it is a feedback gas because its concentration varies with temperature in space and time. So you can see here the symmetric stretch, the asymmetric stretch, and the bend modes are all excitable for a water molecule at various wavelengths. And as if you remember, water has many wavelengths at which it can excite one of these, absorb the photon and excite one of these modes. Okay, I think maybe I should stop here, but let me just show again. We have again the sun's electromagnetic spectrum here, going from shorter, again looking at intensity, about 7% of it is in the strong UV band and longer gamma rays, X-rays, and so on. Visible band is where most of the energy is coming into Earth, and the about 50% is much longer wavelengths, near infrared, far infrared, microwaves, radio waves, AM, and so on and so forth. So best thing to remember is that most of the energy the lower atmosphere receives is in the visible, and a lot of the strong UV, the so-called blue UV, is absorbed in the stratosphere to produce ozone. We'll see that that makes a difference in the temperature profile. If you go from the surface to the top of the atmosphere, the temperature profile is going to be determined by where the energy is being absorbed and so on. And all the energy that is going out from the surface and from the atmosphere is bouncing around, because remember, the surface is getting heated, it's sending energy out to space, but there is a layer of greenhouse gases which are absorbing some of the longer wavelengths because they are greenhouse gases, which means they get warmer and they send energy back towards the surface and out to space. So this is what causes the global warming. You have energy going from the surface into the atmosphere. Atmosphere, because of greenhouse gases, is absorbing a lot of the long wave energy that's trying to go out. So that is going to get reflected back, and then atmosphere is going to achieve some temperature and it's going to send energy out as well as down. So the main thing we'll see when we do the energy budget is that greenhouse effect produces a warmer surface temperature than if you had no greenhouse effect. Okay. The other thing to remember is that the atmosphere has multiple levels from which energy is going to space at different wavelengths, and the key question then becomes at what height the energy is going to go as global warming happens. So we will see that that gets a little bit complicated. So just to close this out, meet the greenhouse gases: carbon dioxide, symmetric, no dipole moment, but it has asymmetric stretching, bending, and rotational modes which can generate greenhouse effect. So CO2 remains the most dominant greenhouse gas. Water molecule, which is permanent dipole moment, is a strong greenhouse gas, but it is dependent on temperature, which is affected by these other molecules. Symmetric molecules like nitrogen, this is again nitrogen dioxide, nitrous oxide. I don't know what's happening to me. Nitrous oxide is a strong greenhouse gas. You can see that it's not symmetric. Methane is not symmetric. Ozone is not symmetric. So these asymmetric molecules are able to absorb outgoing long wave radiation and create absorb energy and create warming. So typically what happens in a simple way, energy radiating from the surface is going out to space, and imagine that there are a certain number of carbon dioxide or other greenhouse molecules, either some that allow energy to go out and deflect it, or just let the energy escape, like N2O and nitrogen and oxygen, for example. But with time we are increasing the greenhouse gases, so the likelihood of energy escaping to space is decreasing. So you can see there is more energy going out here than here, because increases in greenhouse gases, which are these, allows the outgoing energy to be absorbed and sent back to surface and to be trapped in the atmosphere. So remember, we saw how temperature is related to the kinetic energy of the molecules. So as the molecules in the atmosphere absorb the energy and increase their kinetic energy, that's going to increase greenhouse effect and atmospheric temperature and surface temperature. Mars, which has actually almost 8 times the Earth's CO2, actually has a very, very thin atmosphere. It's further from the sun than Earth, so it is cold at minus 50 degrees centigrade. It has a very, very weak greenhouse effect, whereas Venus, which is closer to the sun, has 154,000 times the Earth's CO2 concentration. So it has what is called a runaway greenhouse effect. Its surface temperature is at 460 degrees centigrade. So when we keep increasing greenhouse gases in the atmosphere, we have to understand if Earth is capable of going into a freezing condition like this, or boiling condition like this. This is what we need to understand from past climates, which we did in chapter 3 when we looked at paleoclimate. So we are kind of adding things along. So how temperatures have changed in the past and how they will change in the future as we keep perturbing the greenhouse gases in the atmosphere. That's the main question we have to understand. Okay, so this is a bit a longish podcast, but the ideas are simple, so please make sure you get a grasp of all of these things, because we are going to do a few calculations in the next podcast where we're going to look at radiation energy balance, how much energy is coming in, how much energy is going out, and how that determines the average temperature of the planet, and why that is going to change with greenhouse gases. You already got some idea, but we'll put some numbers behind them. Okay.